Today's video is about the data collection for Lab 3, which is significant digits and density. So you're going to start by measuring a wooden block. So if you're following along in your lab manual, you're going to go past the pre-lab onto page 19. So the procedure has you measuring the length, width, and height of a wooden block. You're going to use the following pictures to get those measurements, and you need to make sure that all measurements are measured in centimeters. Okay, and the pictures will show the centimeter side of the ruler. Make sure that you take into account significant figures, which means when you're using a ruler or any other device, you want to go one past what the device allows. So for instance, if your ruler only goes to the 10th spot, 0.1 increments, you want to go one further than the 10th spot. So you're going to go and measure out to the 100th spot, so 0.01 increments. Let's take a look at the wooden block that we're measuring. So first we're going to take the measurements of the length of the wooden block. So in the top picture you can see the number 3 block that we are measuring, and we're first going to measure the length, the long side of it. In the picture below you can see a close-up of that measurement. So this is the centimeter side of the ruler. So when you are filling in the length in your lab manual, make sure you are putting centimeters after it. Now, looking at this ruler, you can see that it measures to the 10th spot. So each one of these dashes is worth 0.1. So we have 11.1, 11.2, 11.3, 11.4, 11.5, so on and so forth. Okay, so you don't want to stop at the 10th spot when you're taking this measurement. You want to go one further. So looking at this picture close up, it looks like this block is approximately 14.5 centimeters. But you don't want to put 14.5. You want to go one past that. So is it a little longer than 14.5 or is it a little shorter than that 14.5 dash? I would say it's a little bit longer than the 14.5. I'd say it's halfway between 14.5 and 14.6. So the measurement I would write would be 14.55. Now you might have wrote 14.54 or 14.57. That's fine. What's important is that you are keeping the correct number of significant figures. Next, we're going to measure the height. And this time I'm going to leave it to you to decide what exact measurement you want to write. So in the picture to the left, I just show you the total height of the block, going from 0 up to the 9 centimeter mark, and then I have a close-up in the picture to the right. So you can decide for yourself. We're using the same ruler, so it goes to the 10th spot, meaning you're going to want to write out to the 100th spot when you write the length, or I'm sorry, the height of that block. You can pause the video if you need more time to look closely. Last but not least, the width. So for the width, this one's a little bit easier to see. It's nice that we have that clear ruler. So once again, using the centimeter side of the ruler, and it is just shy of 2 centimeters. So whether you think it's 1.90 or 1.91 maybe, that's up to you to decide. So please record the width of the block in your lab manual. Pause if you need more time. Now that you have the measurements of the wooden block, you are going to calculate the volume of the block using the formula length times width times height. Since we're talking about a solid object and you are multiplying the length, which is in centimeters, width, which is in centimeters, and height, which is in centimeters, your units are going to be centimeters cubed. Don't forget to write your units when calculating the volume. Also, make sure you're using the correct number of significant figures. So based off your measurements, since we're doing multiplication, you want to count how many significant figures are in each of those measurements and pick the smallest one. Next, we're going to look at a cylinder. So number 2 of the procedure in your lab manual talks about an engine in a boat with a displacement of 350 inches cubed. That's not going to require any actual measurements, so that's why I'm skipping over number 2. That is just a conversion question for you to work on. So I'm now looking at number 3 still on page 19, and it says using a plastic metric ruler, measure the length, diameter, and radius of a metal cylinder. So instead of using a plastic ruler, I used what's called a caliper because it's a little bit more accurate, especially when measuring things that are round. So what I have shown first is the length of the metal cylinder. And how you read a caliper, I have a close-up to the right here, is you see where this 0 is and that dash mark above the 0, that's where you're reading from. Okay, so you don't want to read along this edge right here because that's incorrect. You want to read from where this 0 dash is. So the measurement, the 6 centimeter mark is this long mark right here. So we have 6.1, 6.2, 6.3. So it's almost to the 6.4, but not quite. So since this caliper ruler goes to the 10th spot, just like the other ruler did, you want to write out to the hundredths. So I would say, since it's almost at the 6.4, but not quite, the measurement I would write down would be 6.39. This last digit is that uncertain digit, so you might have thought it was 6.38 or 6.37. That's fine. The important thing is that you have 3 significant digits that you've went out 2 decimal places. Now let's look at measuring the diameter of the cylinder. So this is the part straight across, the longest part of the circle. So I put the calipers on the widest part of the circle, and then looking at the close-up, remember I'm taking the measurement from where this 0 dash is. Okay, so that's where I want to look. So I'll leave it to you to figure out what the measurement is for that in that close-up. Now remember, this is the diameter. You also have a spot where you need to fill in the radius. So in order to fill in the radius, you're going to take whatever you get for the diameter and divide it by 2. Radius is always half the diameter. Now that we have all the measurements, we can calculate the volume and density of the cylinder. So to calculate the volume of the cylinder, you're going to be using the following equation where we have pi, which is 3.14 on your calculator. You have a pi function most likely on it. R squared, which is the radius, and remember we measured the diameter. So to figure out the radius, that is going to be half of the diameter that we measured. Then you're also going to multiply that by the length. Don't forget your units. Once you have your volume, you can then calculate the density. Now we're going to calculate the density of this cylinder in 2 ways. The way that we're calculating it right now is called the direct method. It's direct because we directly measured the cylinder using a caliper, using a ruler. So in order to calculate density, we're going to use the following equation where density is equal to mass divided by volume. So the volume we have, volume we just calculated above. But what is the mass? Well, in order to get the mass of the cylinder, you need to put it on a scale, which I did in lab. And when I put it on the scale, I got 207.889 grams. So you'll be using that mass in the numerator and then divide it by whatever you calculated for the volume above. Once again, don't forget your units. Next, we're going to take that same cylinder and we are going to measure the density of it once again. But this time we're going to measure it through a process called water displacement. So instead of figuring out the volume of the cylinder by taking measurements with a ruler, we're going to figure out the volume of the cylinder through water displacement. So the way we do this is we fill up a graduated cylinder with a certain amount of water. So you're going to need to record the initial volume of the water, and that is in this first diagram here where it says water level before. That's the initial level of just water. You can see it's approximately 51 milliliters. But just like the ruler, you don't want to approximate. You want to go one further than the device allows. So this device, this 100 milliliter graduated cylinder, goes by ones, right? 51, 52, 53, 54, 55, all the way up to 60. So if it goes by ones, you want to go one further, which means you want to go one decimal place out when you're recording the initial volume. And I'll leave that decimal place for you to decide what value should go there. Once you record the water level before, the cylinder is then added. So that's what you can see in this middle picture here. You can see that metal cylinder in the graduated cylinder. And notice the water level rose. Before, it was around the 50 mark. Now it's way up here past 70. So once you put the cylinder in the water, it's going to displace the water or move it, making room for the cylinder. So you can figure out the volume of the cylinder depending upon how much water was displaced. So what I have in this last picture here is a close-up of the water level after the cylinder was added. So looking at the meniscus, here you want to record, make sure you're going out one decimal place, the new level of the water. Here's another picture with a piece of paper behind those two water levels. So if you were having trouble seeing, especially in the after picture, I feel like it's a little clearer with the paper behind it. So this second picture here is the after. You might be able to see it and record more accurately using this picture. So whichever one you can see more clearly, use that one. Once you have the before and after water levels recorded, you are then ready to calculate the density of the cylinder through the water displacement method. So to do that, you're going to calculate first the displaced volume. Once you added that cylinder, how much water was displaced? So you're going to take the volume after, subtracted by the volume of the water before. Subtracting those two numbers, that's going to give you the volume of the cylinder. So now you're going to calculate the density of the cylinder once again. You're going to use the same mass from the previous slide, that mass of 207.880 grams. But now the volume you're going to use is the volume that you just figured out above by subtracting the water level before from the water level after. Now your density is calculated using the direct method, which was using the caliper, using the ruler, should be very close to the densities that you're calculating here using the water displacement method. They should be very close to one another. We're just utilizing two different methods. Now we're going to do the water displacement method again, but this time we're going to do it for a rubber stopper. So you can see in the picture above the black rubber stopper. So with a rubber stopper, it's an irregular shape. So we can't use the direct measurement method with it because it's not a perfect cylinder, it's not a perfect cube. We don't have a volume equation to use to calculate that shape. So to figure out the volume of a rubber stopper, the only method we have available to us is through the water displacement. So it's much like with the cylinder. I have the first picture here is the water level before, and it's a little above the 50 line. Make sure once again you're going out 1 decimal point. Then the rubber stopper is added. You can see the rubber stopper here at the bottom of the 100 milliliter graduated cylinder. You'll also notice that the water was at 50 initially, and now it has risen this amount here. Now we have the water level after, so it's not quite at the 60 yet, it's right around the 59 here. So record the water level after as well. And it's nice for this one because there's a data table that gives you the volume of the water organized nicely. A little bit easier, more clear. Now that you have the data that you need, you're going to calculate the density of that rubber stopper. So to do that, you're going to take the volume after adding the stopper to that graduated cylinder and subtract the volume of the water before adding the rubber stopper. This will get you the total displaced volume that was caused by the rubber stopper. This volume that you calculate, you're going to be using that as your V value in the density equation. Remember, the units on volume are going to be in milliliters since we are measuring water displacement using a graduated cylinder, which is measured in milliliters. For the mass portion of this equation, you're going to be using the mass on the previous slide of the rubber stopper, which was 15.292 grams. So you'll take that mass divided by the volume that you saw on the previous slide due to the water displacement, and you'll get your value of density in grams per milliliters. Don't forget your units. So we're going to end with a final question. Why can't we use the direct measurement method to determine the density of the rubber stopper? If you're not sure the answer to that question, you might want to back up and listen to the previous slide. Let me know if you have any questions.